So actually, before we get going with the research presentation and discussion today, I and the IARPC Glaciers and Sea-level Collaboration Team would like to just briefly respond to current events. So in order to collectively tackle the challenging physical science problems related to land ice and sea level processes, we must likewise acknowledge challenging social problems that confront individuals on our team and the society that we live within. Therefore, before we proceed with the next hour of discussion and inquiry on interactions between the solid Earth, cryosphere, and sea level fingerprinting projected by various glaciers and glacier and ice sheet models, I felt it to say simply and plainly that Black Lives Matter. So thank you all for joining the webinar today, and thank you, Eric, for agreeing to present. We're all looking forward to what you have to share with us about sea level and model sensitivities. Another quick reminder related to business, Joe and I are still seeking feedback on the Glaciers and Sea Level chapter of the IARPC 5-year plan. So Kelly, if you could click on that 5-year plan link. We've got a little post on the IARPC website. So Joe and I will be accepting team member input for another couple weeks until June 30th. So we have this Google document, which is that other link, Kelly. And it's 5 pages. It presents an opportunity for this team to represent our research community and research needs, to communicate crux knowledge gaps to the US federal government officials who envision and formalize how American resources will be directed towards Arctic research. So check it out, give us some feedback. And with that, we'll turn it over to Joe to introduce our speaker today. Thank you all for attending.
Sure. Thank you, Caitlin, and thank you for drafting that statement and sharing that. I think that's also very important that to share with everyone here, especially in this time. I noticed in the document that Kelly was showing that it was there was a little pop-up that said this document is too long. My goodness, it's only 5 pages. That's I've never seen that before. I don't know what that is about, but as a writer of long papers, as many of you are, I'm a little offended. Yeah, so we're very happy today to have Eric here to tell us about his work that's been ongoing for several years now while he's at NASA, and about concerning sea level fingerprinting due to changes associated with Earth's ice sheets, glaciers. And so Eric, he actually introduced himself here perhaps better than I could immediately in the group chat, but he's the lab chief for the cryosphere. I'm not going to get the group title correct. The cryosphere group and sea level ice at NASA's Jet Propulsion Laboratory in Pasadena, and he's been studying this particular topic for several years. And Eric, are you a part of the sea level change team as well?
Yes.
Okay. Yeah. So and with that, I think we'll turn it over to Eric and learn what he and his colleagues have been up to. So
thank you, Joe.
Kelly,
Oh yeah. Let me see. Should I share my screen now, Kelly? Okay. So let me find my PowerPoint. There it is. Okay. Can everybody see my screen right now?
Yes.
Okay.
Looks good.
Sounds good. Thanks, Joe, for the introductions. Joe kind of upped the title a little bit. I don't remember sending this title, so it's fine. We can blame glaciers here. I love it, actually. So I'm going to just present some of the work, as Joe was introducing, about how we can basically understand the sensitivity of sea level rise and the contributions of different inputs, such as glaciers, ice sheets, glacial isostatic adjustment, also GIA. I will not go really too much into the details of ocean steric effects here. I think Joe and I thought, keeping it at the ice level would be a good idea. So this work is a collaborative work in our group. I've kind of cited the folks that are working on this. I'm probably forgetting other collaborators that have given us some ideas, so apologize for that in advance. We have Lambert Caron, who's really the expert in GIA, with Eric Ivins and Surendra Adhikari. Matthew Mulligan has been helping me tremendously improve the engine behind the sea-level computations. And Surendra Adhikari has been behind the theoretical development for that sea-level computation. Thomas Frederiksen and Ben have been helping me a lot in terms of understanding the dynamics of steric and ocean circulation effects on sea level, and Helen Searcy, of course, for the ice sheets and the angle for ISMIP6. So really kind of a group effort here that I'm presenting. So I will go basically and try to understand the sea level projections in terms of sensitivity to the model inputs. I will not really expand too much in terms of probabilistic projections this time around, because this work is really starting. ISMIP6, GlacierMIP2 have released results, and everybody, I think, is going through the difficulty of introducing these model inputs into their frameworks. And I think it's a little bit premature right now to really kind of draw conclusions, but I think preliminarily, there's a lot of things we can look at in terms of sensitivities, and that's really the angle here in my talk. So I will introduce, therefore, a tool called gradient fingerprint mapping that we've worked on for a while to understand these sensitivities. And I will look at how we can use this tool to really quantify the contribution of glaciers, ice sheets, and GIA to local sea level anywhere in the world. So as a background, I'm looking here at the results from the latest paper by Steve Neeram, 2018, on really understanding 2018, yeah, maybe a little bit more recent, measurements of global mean sea level change from satellite altimetry. And of course, seeing this kind of beginning to see the trend develop here, and Steve taking a look at how we can really start quantifying this with maybe potentially a quadratic kind of acceleration term here. But I think I want you to look at this in terms of, we really have a pretty strong trend, some interannual variations along that trend, definitely a rise in that trend from about 2 to 2.8 millimeter per year, 20th century trend, to now 3.4, 3.8 millimeter per year, and accelerating with short-term cycles combined with long-term glacial trends. So definitely something we need to look at and address from at least the model projection side of things. A lot of challenges there that this curve actually and this graph involves here. Confirming in terms of the patterns spatially here associated to that trend. Thanks, Felix, for forwarding me all these graphs from the GraceFO website, and so credit to the GraceFO science team here for this. You see here the latest 2020 March surface mass anomalies, and what you're looking at here is really the impact of on land. You have the terrestrial water storage and water drawing down. You look at so in red, an increase potentially also of water TDWS on land. You have the bottom pressure fingerprints here, not fingerprints, patterns in the oceans. And of course, what really stands out to me is the impact of glaciers and ice sheets, Greenland, Antarctica, as the waste area, West Antarctica ice sheet, Alaska, big pattern there, and Canadian Arctic, Greenland. Really standing out here that we need to take that into account for sea level projections. If I go and look at, again, really nice visualizations that Felix put together with the Grace team here and GraceFO also, we have like these patterns for Greenland of melting and ice flow dynamics too, lowering, basically decreasing the mass of Greenland. You see the impact of very large basins, Jakobshavn, Helheim, Kangerlussuaq in the south, Very strong patterns there, and same kind of interannual variations driven by a lot of the surface mass balance variations, but also a significant trend in terms of the ice flow dynamics here and the drawdown of all these basins, with a very severe average mass loss of 281 gigatons. If you wanted the ballpark number, 361 gigaton per year is a millimeter of sea level if you take like a bathtub model. So we're dumping about 0.8 millimeter per year from Greenland right now. That's a very significant amount. Looking at the same pattern here in Antarctica, average mass loss 2 decades ago that has really increased severely in the last decade, confirmed by ISMIP2 results recently. 125 gigaton per year average, 0.3, 0.4, probably increasing right now if you took the trend over the last 10 years only. Very severe patterns of ice flow dynamic loss in the West Antarctic ice sheet region. Can you actually see my cursor if I move? Can I use that? Kelly, can you confirm maybe?
Yeah, that works.
Yeah.
Okay, cool, nice. And as expected also from some papers, for example, from Bunning et al. In, I forget the year, precipitation increases in the East Antarctic ice sheet. So you have this very strong pattern peninsula losing a lot of mass. This will have very severe ramifications in terms of sea level because of an effect that we'll go through later on, the rotational feedback, which basically will impact the east coast of the United States more than other spots in the world. So if you look also at glaciers, I'm here showing the latest results from Zemp et al. In Nature, where you have very significant contributions from Alaska, 3,019 gigatons since 1961. Once again, you're talking about 360 gigatons for 1 millimeter per year of sea level. So here we're talking close to about 0.8 meter, sorry, let me see, divided by this by 10. So we're talking 8 millimeter of sea level from Alaska. Very significant patterns here. The only area that is really increasing in terms of mass loss is the southern part here of the Himalayan area, the zone. All the zones here are the RGI zones that I will actually use for some of the projections. They're basically defined according to the RGI Randolph Glacier Inventory. And I want you to take away from this the very kind of distributed mass loss patterns here that we will take into account for computing sea level patterns around the world. And so it's quite a challenge to be able to handle all of these different mass changes. In terms of the processes that we will try to assess here, I don't like to talk about fingerprints. I think we should start looking at sea level patterns and GRD sea level patterns, GRD standing for gravity, rotational, and deformation. What you have when you look at a sea level model, you have the classic assumption of what I would call the bathtub model. Whatever ice mass is lost is basically dumped into the ocean, and the sea level rises by an equivalent amount. Now, that's really not what happens in reality. When the ice is being dumped into the ocean, the gravity field here decreases, the local gravity field, which tends to therefore repel the water away from the mass loss. And so you get a little bulge of sea level far from where the ice was lost, and locally a decrease in relative sea level. And you will see these in the patterns of sea level that we computed. If you look at adding on top of that what we call the elastic rebound, or a long-term trend of glacial isostatic adjustment, GIA rebound, you get a terrestrial uplift as the ice thins. And so this draws mental mass into the area of terrestrial uplift, tends to decrease sea level on a relative basis, RSL. And so this is a really significant process when you have very fast mass loss. And the elastic uplift here can actually be quite significant. We had a publication last year on its impact on grounding line dynamics in Antarctica, if you're interested in this process. As I was saying, the rotational feedback of the loss around West Antarctic here is really significant on the in a pattern that is determined by what we call the rotational feedback. And if you think about a spin top, when you have mass loss, the axis of rotation tends to get modified, and so this engendered this creates a pattern of sea level that has these singularities. Oops, sorry. Here and here, you can see these two dipoles here. And so that will create a sea level pattern that is very different. And unfortunately, when you see the mass loss of this bedrock that is under the ice, so this is an area that is very prone to instability, and that's where all the mass loss is happening, like we saw in the grace patterns. This tends to actually accentuate those dipoles, therefore has a significant impact on sea level patterns in the US. And so it's quite relevant here. When you put all of these things together, the picture gets complicated on what drives sea level patterns. If I'm looking at an initial, very simple model that was created, actually not a very comprehensive model, but the Pharaon Clarke equation, when you look at it from basically an angle distance from the mass that is creating the sea level, relative sea level increase, you had these very simple solutions that would give you an idea of the evolution of sea level away from mass that was losing ice. So creating sensitivity maps out of this kind of formula was extremely easy. The problem is when you add uplift, when you had rotational feedback, complex SAL into you start losing the simplicity of these formulas to compute sensitivities. And so you're really losing grasp on what really controls sea level patterns from the source point of view. So to reestablish the capability to understand these sensitivities, we created this tool called gradient fingerprint mapping. So to do this, we first needed a computational solver, and Surendra Adhikari worked a lot on the theoretical construct that allows you to basically use an unstructured mesh like this one, very refined in areas where you have mass loss, for example, in the Alaska glaciers, around Greenland and the Arctic, etc. You don't need such refinement on the oceans themselves unless you're looking at bottom pressure fingerprints. When you have such a mesh, you need to start mapping these Pharaon Clarke equations into that unstructured mesh, and this had never been done before. The classic methods was to approach the equations of Pharaon Clarke using a spherical harmonic decomposition, which is done on a regular grid, except we were really trying to look at Greenland and Antarctica in detail. And so we just needed to switch our approach. And what we did was basically use a convolution of the sea level equation, and that's the convolution with a green kernel function here, against a load, which is the ice load. The rotational feedback comes here. I don't want to go into the detail of these equations, but basically Surendra was able to redraw this theoretical construct and to map it into an unstructured approach. If we use the ISSM system to do this, we would then gain the advantage of being able to model ice sheets and at the same time understand the sea level patterns emerging from these ice sheet changes. We did this using parallelized MPI coding with a C++ code based, heavily anisotropic mesh adaptation. And this gave us really access to the data assimilation capabilities. And that's the key here. We wanted this gradient fingerprint mapping to understand sensitivities. And so once we use this sea level solver that, for example, out of an ice sheet mass loss here generates a sea level fingerprint, when we do this kind of solver, we go from the ice sheet loss to, for example, for Iceland, sea level locally on the coastlines of Iceland. But we wanted to go reverse. We wanted to understand when you're sitting somewhere on the coastline, or in the middle of the ocean, what is actually hitting you from where? What is the contribution of each glacier loss in the world to sea level where you are sitting at? So we wanted to go the other way. We wanted to know the direction of these arrows and how big these arrows were. That's what we call gradient fingerprint mapping. And the only way to do this was to basically use automatic differentiation of our sea level solver to figure out the gradient of sea level in, for example, Iceland, with respect to ice changes everywhere where there is ice. So automatic differentiation is a technique that uses that C++ code that we developed and automatically computes that gradient. And so using this, we can get exact higher order derivatives at double precision of any of the model outputs to the model inputs. This is exactly what we wanted, those green arrows going backwards. And so when you do this, you compute derivatives. And so here's a pattern for the city of London of sea level. So you'll see several times in the talk, sometimes I talk about sea level in a certain location where there is no sea. Well, the concept of sea level is really here. An extension into the continent can be an extended through the geoid. So to me, it doesn't make a real difference. Now, the only difference is that the geoid has to be adapted so that the amount of sea level conserves mass in the system. So if you take London, you can still compute a pattern of sea level there. Well, through the Thames River anyway, will be locally adjusting. And you see sea level, derivative of sea level with respect to ice loss everywhere in the world. No ice loss means zero derivative. And here, what's really interesting is you see patterns that match a little bit of our understanding. The further you're away from the ice, the redder it gets, which means there's a strong contribution of this ice mass loss to sea level in London. But if you look at, for example, from London going to Greenland, you realize that the sea level contribution of East Greenland to sea level rise in London is really small, almost zero. You have to go literally to the west of Greenland and the northern west actually of Greenland and the Canadian Arctic to start really seeing a contribution to sea level in London. So that's really an interesting reversal where you can really understand that the further away you are from the ice, the more that ice losing its mass is going to hit you. If you look at the gradient, it's bright red for Antarctica. So Antarctica really contributes a lot of sea level rise in London. Now, the amazing thing too is that that gradient can turn negative. And so if you took a look at the New York gradient, it's negative in the south of Greenland, which means that mass loss in Greenland contributes sea level decrease in New York. And so this gives you really a different point of view. You're reversing your point of view and you're trying to figure out from a locality or a city, or even if you're in the middle of the ocean, you might be interested for a tide gauge or a weather station floating on an Argo buoy. You want to know what's going to really contribute to sea level locally. So we did this for every city in the world that had also a tide gauge location. And when you look at, for example, northern continent of America, you look at all these cities. As I said, if you take New York, the gradient turns negative about, the line is about here. And for Nova Scotia, it's even more south. So what you have here is basically the entire Jacobshavn Glacier is basically contributing sea level decrease in Nova Scotia, which is quite a twist for me to understand this. I'm still wrapping my head around it. And the further away you're from Greenland for the US coastline, it would be in Los Angeles. That's where it turns the most, the mass loss is impacting the most. Now, this is really an interesting concept because you start seeing that you can understand the contribution of every one of these little glaciers in the world to sea level in your city. And what then the next step would be to understand in percentage, you know, how much percentage of my sea level is due to Greenland, Antarctica, Alaska, etc. And so that's where we want to move into. That space, I think, is really important to understand. Even for local city planners or coastal planners, they really want to understand which part they should be monitoring to and how that those parts are relevant to their city. Another thing that I wanted to convey is the fact that the gradients, they can reverse sign, but they also change magnitude over quite short distances. And so in my opinion, there was this kind of misconception that fingerprints are a global pattern and they kind of vary over thousands of kilometers. They don't. It's 100 to 200 kilometer. And so if you look at Nova Scotia versus New York, you can see that Jakobshavn is going to impact these two cities quite differently. And so you really have to kind of look a little bit more into the detail. I would think that the GRACE resolution is the type of resolution you want to look at. And so that's kind of a ballpark number, 300 kilometer. There were some really nice applications that were picked up. And this is the most graphically compelling one I've seen so far, where they were looking at the impact of GIA on sea level rise in Reykjavik, Oslo, Stockholm, Helsinki, and the impact of the other masses of ice that were being lost. And you start seeing really compelling, you can understand really quickly what's driving what here. If you're in Reykjavik, you're looking at GIA and Greenland ice sheet as really the two things you need to monitor. And so that's quite significant. This becomes more or less relevant for the cities in Europe, Northern Europe. And so it really gives you a good point of view on what's really key to understanding your local sea level. GIA in Sweden, Norway, Finland is it. You need to look at this. It's the main thing. Now, it's not exclusive, but the proportion here is so large. So this is something that really kind of resets people's expectations of what's driving sea level. So GFN can be used to assess observations, but it can also use against model projections. Here are some of the graphs that I picked up from our paper 2 years ago, using the sea rise forcings. And so you can basically extend your understanding of what drives sea level in New York, Oslo, or eustatic, so the GMSL in the entire world, what drives this according to, for example, if we take just the Greenland ice sheet, every area in Greenland that drives sea level in New York are basically in red here. And so as expected for New York, the northern, east and western part of Greenland are really the ones that are the most important. For Oslo, you look at this, it's totally different. Really, as I said, the eastern part of Greenland is really not contributing or negatively contributing to sea level rise in Oslo. And this is, if you were sitting really far from the ice sheet, every part that is losing mass is really hitting you. Is there any questions at this point, maybe? Because it's quite a bit to take in. Okay, I'll keep going then. Here it shows the degree of accuracy we can reach. And again, we just grabbed some of the graphs from our paper 2 years ago, where we just basically grabbed 4 glaciers, 4 big basins in Greenland, and we multiplied the gradient fingerprints for cities around the world. Basically, we convolved them with the mass loss from all of these 4 basins. And so you can now understand the contribution to your local sea level from every one of these glaciers. You could actually do this from one specific glacier if you want, a tiny glacier anywhere. And so you can compute these in about 2 seconds by multiplying the load by the gradient. It's just a simple multiply of 2 vectors. It's very, very fast, and you can do really quantifiable assessments of basically a budget of sea level for your local city. Now, what's great is potentially pushing this understanding of sensitivities, as I was showing here, through projections. And so what the community right now is trying to do is grab the latest results and basically redo this kind of analysis, either using this type of uncertainty approach, using a joint base projections, or using probabilistic approaches. I'm not going to, as I said at the beginning, show probabilistic approaches, but I want to kind of start looking at the details of what the latest results show us in terms of sensitivities and doing this kind of budget. So the way we're running these projections using the CISO product that was developed by Surendra, and we integrated this in ISSM. The way you look at this now is not this kind of approach based on fingerprints from Antarctica multiplied by the mass of Antarctica plus fingerprints of terrestrial water storage multiplied by the drawdown in this water and terrestrial water storage, etc. You do this for glaciers, for Greenland, Antarctica. You add to this a dynamic stereo component and a VLM, which is the vertical land motion. You put a big giant plus and you get your RSL. That approach to us is kind of not making it possible for us to draw these sensitivities. So we switched to this framework where we're directly inputting these thicknesses changes in the terrestrial water storage, Greenland, Antarctica, glaciers. We can also include the impact of bottom pressures, and we include GIA RSL directly, but we compute this through a sea-level system solver and to compute that GRD pattern. And so this way we don't break the chain, and we're able to kind of follow the sensitivities across the entire system. And so as it says here, is we're really trying to replace an integrated model diagnostics that was run through fingerprints into a more granular system where you could capture ice thickness at, as I said, 200 to 300 kilometer resolution. And the beauty of this system also is that it allows you to plug in directly things that compute thickness changes. For example, ISMIP6 results. You could have, for glaciers, you could have the GlacierMIP results. And I'll show that we can integrate GIA statistics in here. So different GIA models if you want. When you do this adaptive meshing that I was showing previously, the beauty of this is that you can really zoom in here on the RGI Randolph Glacier for the Patagonia and ice fields. And if you take, for example, a GRACE observation of mass change in this area, you can use it to refine your mesh. And so what you're going to drive is really a way to capture the load, the ice thickness change in your sea-level solver. And you can also ensure that the coastlines are fully represented. And maybe not easy to see here, but this GSHG coastline from the Hawaii Center on Sea Level are fully captured by this mesh. And so at a resolution integrated directly into the mesh. And so we make sure that we capture coastlines at very high resolution using this approach. If you look at the challenge to us was to really capture, the most challenging part was really the RGI glaciers. So the Randolph Glacier inventory has, I believe, 200,000 glaciers in the world. And you want to capture that in a certain, I mean, you want to capture the positioning of these loads. And here we're targeting a 40 kilometer resolution positioning of these loads. And so what we did is we started refining our mesh. You can see the global mesh, the oceans, because we were not focusing yet on bottom pressures. We did not really refine the oceans. When you zoom in on the Greenland ice sheet, you kind of get an idea of what the resolution of your mesh is. When you blow this towards the Canadian Arctic, you see how we try to capture the glaciers. You have connections between oceans here, so sometimes the mesh gets a little bit funky. We captured all the coastlines of Greenland where the main mass loss was going on, and we targeted really these areas. And it's not easy to capture all these glaciers. This gives you an idea of 3 zones in the RGI glacier inventory. We wanted to really capture every single one of them, at least in terms of the mass that they deliver to our sea-level system. And this is actually quite tricky. I show a blow up of one of the glaciers here. You are hitting this sea-level solver with 40 kilometer meshes. A lot of these glaciers don't even align with any of these triangles. They're really sitting in the middle of these triangles. So now what you're going to want to do is really understand how much area of this glacier this triangle here owns versus this other triangle, etc. And you're going to have to do this for every glacier in the world. Otherwise, you're going to start losing mass when you transfer
No worries. Congratulations to him. This is the nature of the time, so carry
Yes.
on.
So the key here to doing this mapping of areas correctly is that you're going to not lose any mass. And so you can think about it as a downscaling algorithm that conserves mass through conservation of areas with different projections also involved between these. And so imagine the complexity of running this algorithm with about 200,000 elements in my mesh and 200,000 of these glaciers with different shapes. So that's why it took quite a bit of adjustment here to grabbing the GlacierMIP results. And also the ice sheet results are mainly on the ice sheet inland, but you can see that the Randolph Glacier inventory has a lot of glaciers in the periphery of Greenland, which in the ISMIP6 results, so the intercomparison project for ice sheets, they're generating changes in ice over this entire ice sheet, and they really kind of encompass also what was considered glaciers from the RGI point of view. So you have a big risk of double counting here. And so what we did also through this algorithm is exclude the areas that were in the ice sheet interior from the RGI glacier inventory, and vice versa, exclude the glaciers that were truly in the periphery, like this one, of Greenland from the ISMIP6 results while we're doing this downscaling. So it takes quite a bit of effort to run this. Actually, the bulk of the computation is really about that downscaling. The sea-level fingerprint takes about 2-3 seconds pure time step. So that gives you an idea of where the computational difficulty lies. Once you've done this downscaling, you can really start looking at the results, and it's very interesting. We have the GlacierMIP results that have just been published, Marzion et al. In 2020. And so thanks, Ben, for sending me these results and allowing me to use them right away. I've plotted our reproduction of figure 5 from Ben's paper. And we have all the trends for every zone in the RGI Randolph Glacier inventory, so 19 of them. And here you have the global trend. In red, you have the RCP 8.5 scenario, and in blue, the 2.5 scenario. They've done a real large ensemble with about 200 glacier models, sorry, not models, 200 glacier runs with that many models running, about 10 or 11, I think, and that many GCMs forcing these models for the 4 different scenarios in CMIP5. And so you can grab the statistics of these, or you can grab the mean trend. I will show the mean trend here to really force the sea level GRD pattern computations. But you can see the potential here for doing some multi-ensemble analysis, grabbing some of the statistics to inform future projections. So that's where we're moving. I'm going to use these results here to understand the sensitivities. The other inputs that we wanted to feed into, Joe and I decided that we would kind of keep it at ice. So I think what we really wanted to see was the impact of the ISMIP6 model runs. I've grabbed here the results from Helen's paper that was just accepted. And the Heiko's paper is still in review, I believe. Correct me if I'm wrong, Helen. And so I grabbed your figure here to show the spread in model runs. These ones were forced by the NOR-ESM RCP 8.5 scenario. And so one of the difficulties here is that these runs are sensitivity runs against control runs. So they are not fully capturing trends, mean trends in sea level rise. They're still very, very interesting to understand statistics of how the models behave. In addition, we grabbed a GIA model statistics analysis from Lambert-Caron, where here you're seeing the mean map of the geoid rate from 5,000 runs carried out in a Bayesian inference framework, where Lambert was trying to match GPS stations and other measurements of sea level rise in the past, like shoreline migration to best fit GIA models. And so what you're seeing here is the best likelihood of these model runs. And so this is really a probabilistic framework in nature, and we can grab that mean trend and put it in our runs, but we could also use the standard deviation of this ensemble to really understand the statistical content of these models, and which models are outliers, which ones are really more representative of the best fit to observations. When you do this, in summary, I grabbed the Greenland ice sheet, Antarctica ice sheet contribution from ISMIP6. We grabbed the GlacierMIP2 results, RCP 8.5 mean trend. We downscaled all of this in a mass conserving approach, and we run these, and here's what we get. And once again, don't be surprised, Greenland will not show up as a big spot because ISMIP6 was really trying to target sensitivity runs against control runs. I mean, it still shows quite a bit of signal. And here you see a big impact of the GIH statistics after 100 years, but you definitely see the glaciers kicking in and Greenland kicking in. And so this is just for this area. I don't have a movie for the other parts close to Antarctica, but you get these runs carried out over 100 years, and then you can use these with gradient fingerprint mapping to understand contributions. And so here things get really interesting in my opinion, and maybe I'll just leave this at the end so that people can ask questions. What I did here is I grabbed all the RGI glaciers, distributed in these 19 areas, and I created pie charts of which ones are impacting sea level rise in 10 different cities around the world. I overlaid this on the RSL pattern contributed by just the glaciers. So you see there is no Greenland coming in here, or Antarctica. And so you get these very interesting patterns where you start seeing these SAL effects kicking in, and you can really understand which area is important to you. If you're in Hawaii, Alaskan Glacier, Arctic Canada, pretty important. Kind of, as you expect, Himalaya sitting quite far, small contribution. But what you're seeing here is an aggregation of the load plus the sensitivity to that load. So you could imagine, for example, that you were sitting literally by Alaskan coastlines. There, even though the contribution of Alaska is small to the global RSL, being so close would decrease sea level locally. So that small contribution becomes important. So this is a mix of both the sensitivity and the magnitude of the load. When I go here to the next plot, what I did here is the same analysis, except I took all the components of GIS, Antarctica, GIA, and all the glaciers. And what you see, as expected, is the impact of Greenland far away from Greenland really takes over. The closer you're from Antarctica, the less you're impacted by Antarctica. So you see this brown part actually increases far away and decreases towards Antarctica. And then you still have GIA churning along everywhere in a kind of a constant way, with a bigger component the closer you get to the Laurentide ice sheet or the Finoskanian ice sheet. So these charts, I don't think I've seen them before. Maybe I'm wrong. Maybe we're redoing things that have already been done. But this is quite, I think, a significant result in terms of exact quantification of the exact percentage of each one of these contributors. We are currently working on extending these to include bottom pressures, and we'll definitely also include the dynamic and steric effects. And so this will be a deliverable for the sea level science team at NASA, and will definitely be hosted on the servers. So I think we'll be able to really inform people of how they should see local sea level where they are. In conclusion, we have new model projections from GlacierMIP2, ISMIP6, ISMIP6. There's still a lot of work to integrate them into sea level rise frameworks. We're working actively on doing this. There is, I think, a significant need to do this using frameworks that don't break those sensitivities, or basically the tool suite of models need to be compatible with sensitivity analysis and definitely with probabilistic approaches. Our anisotropic meshing and area conservation in ice thickness changes allows us to do that. We really need to understand the double counting efficiently so that we just don't really kind of, well, double count, which would be catastrophic. And I never understood how computationally intensive this is, but it's really the bulk of the work. Now, the good thing is it only needs to be done once. Once you have these conditions met, you can do gradient fingerprint mapping, and you can really quantify relative contributions to sea level from every source, no matter how small it is. And so that allows you to reverse the point of view, right? Don't see this as just a forward model from the ice to the local city. Just you can reverse that. And once you do that, you can really see the impact of self-attraction and loading and rotational feedback, which are essential in understanding the contributions. As you saw when we went around the East Coast, West Coast of the US, things really were totally different from the Greenland point of view. A lot of more research needs to be done to understand the probabilistic ramifications of all these ensembles that are being output by the ISMIP6 kind of galaxy of results. And we need to go beyond forward deterministic models towards probabilistic models, without forgetting that the forward deterministic models are the ones that can give us that true sensitivity. I will stop here. I think I've talked enough. I'll go back here if people want to look at this and maybe ask questions. Thanks a lot for inviting me to this seminar.
Yeah, awesome. Thank you, Eric. That was an astonishing array of work that you've shown, and truly impressive, all the way from slicing up that poor individual RGI glacier correctly to ensure mass conservation, all the way up to the global ramifications. And of course, you reminded us of the reliability of Southern California weather. So thank you. I've got a couple questions. I see at least one from Twyla, brief from a slide earlier in the audience, and we'll sort of open it up first. If you use the hand up signal, that'd be well. First, could you answer Twyla's question from that table that you showed about halfway through the talk?
Let me pull the chat. I don't think I have her question.
Okay. Or Twyla, you can say the question if you'd like.
Yeah, hi, Eric. Thanks so much. I adore this work that you guys are all up to on this. Yeah, and on this was the one I was just wondering what those percentages are, so I can be a little better at reading this table.
Yeah, so this is just the ice contribution, so you have to be careful with the percentage here. If I take RSL at a certain city, that percentage is really what hits you, and they can go above 100% because you can have because of that SAL effect. So what we're looking here is the percentage with respect to what the GMSL contribution should be, would be, if your city was lying very far away from. So another way of looking at this is the bathtub model. How much sea level would be raised by that glacier losing that much mass if you were just dumping the water, the ice into water, and it raised sea level everywhere the same amount.
Okay. Does that answer your question, Twyla?
Yeah, and let me make sure I understand correctly. So for example, with New York, that 62% is telling us that it's a lower contribution than the bathtub model, because the bathtub model would be 100%?
Yeah, it would be, I have it, the number is here, 8.22%. Oops, sorry, my mouse. So what the bathtub model would dump would be 8.22 centimeter, and you see New York only gets 5.1.
Excellent. Thank you so much.
Cool. Thanks. Good question. Vivi Catherine Pedersen asks, what kind of Earth model are you using for the gradient fingerprint mapping?
So only elastic uplift. So we use basically a standard prem model with a standard love number computation, one-dimensional, using so one-dimensional model with a prem parameterization, pretty classic. We recover the love numbers at 10,000 degree harmonics, sorry, 10,000 degrees, yeah. and we are able to convolve these love numbers locally. At 10,000, you are dealing with a resolution in your uplift of about laterally 1 to 2 kilometer, which is probably going beyond what the PREM model can withstand. But our goal was really to understand very local uplift generated by sea level patterns. And I would refer back to our science paper last year on why we needed that much resolution to understand vertical uplift close to the Thwaites grounding line migration area.
Okay, thanks. Chris asks, how do you envision this framework interfacing, interacting with other non-ice contributors to sea level rise, e.g. stereodynamic? And could you explain what stereodynamic is for those of us who are less familiar?
Absolutely. So maybe the best would be this graph here. So we actually currently, I'm currently, for example, computing sea level patterns coming from the bottom pressures that are resulting from ocean dynamics, creating these bulges of bottom pressure at the bottom of the ocean, which have to be computed because they result in sea level patterns that need to account for all these geodetic factors. So the dynamic and steric, the steric component, I would say the STR term here classically would be the global mean sea level trend generated by the warming of the ocean. On top of that, you would have ocean circulation generating a dynamic sea level that you would account for here also. And the last one, as I said, would be the dynamic sea level is going to generate bottom pressure patterns that will result in a fingerprint computation. Those three are currently integrated into ISSM, but we do not envision doing online coupling, for example, between ocean circulation models and our sea level solver. Potentially doable, but I don't think it would yield too much. We're more interested in fully coupling the ice sheet, Antarctic glacier models with online full coupled models, because we own these in ISSM also. I would say currently we're working in the science team to understand how the terrestrial water storage could be input into our framework. This doing this with a full coupling seems to be outside of the range of possibilities currently, but there's a lot of work being done by David Brown's in the science team to understand the terrestrial water storage evolution in the next century with a correct water retention from populations. And so it will still be done offline. So if I summarize, you'll have the hydrological part, the bottom pressure part, and the dynamic and steric sea level done offline, probably coming from ISMIP5 type runs. We will also run ISMIP5 and ISMIP6 forcings for GIS, Antarctica, and glaciers, but we'll probably fully couple those three latter components in the future. GIA, we're actively working with Lambert to do a full GIA integration into ISSM of GIA capabilities. So they will be one and the same because they're just too close to the sea level solver itself to be completely done offline. It just makes no sense. So I hope that's a long-winded answer. I hope it met your needs.
That was a good answer. Maybe if I could ask well, not quite a silly question, and then perhaps a harder question. So is there a glacier that's always bad news? And I'm thinking, for example, of Denman or Lambert Glacier. Are they always they're in East Antarctica, they're pretty much far away from everyone. Are they always inducing a relative positive sea level rise?
Okay, so that's there is an unfortunate city. Let me see, where is it? Do I have the fingerprint for it? So another way of looking at it is, if I want to reframe your question, the best way to look at it is there a city whose gradient fingerprint is the opposite pattern of the mass loss, at which point you get a double whammy, a really bad one, which is that, and there is in South Africa, there is a city that will get the maximum sea level rise. Why? Because they're sitting close enough to Antarctica that the East Antarctic increase in mass results in mass and sea level increase in South Africa. And the sea level loss from the Wace ice sheet also results in the sea level increase. That is truly the worst place. Because when you have the mass loss pattern from Grace in mind, it looks exactly like their gradient fingerprint reverse. And so it's really unfortunate. Mass loss in West Antarctica results in sea level decrease, and mass increase in East Antarctica also results in sea level increase. So this is the only city I can think of. Your question was more which glacier, but I'm more interested in which city has the worst outcome, and why is that? I was always wondering why along the South African coastline you had the maximum sea level rise always, and that's the reason why.
Okay, thanks. I have another question, but Fabian has one. Fabian, do you want to pose the question? On mute. All right, I'll read it. From a glacier modeler perspective who took part in the study, the glacier scale Ben Marjan 2020 results are highly uncertain. Does it still make sense to have a fingerprint mesh at a high resolution when the single glacier estimates are, his words, let's say it crap?
So I'll harken back to David Rounce's work on HMA here for Himalayan glaciers, and oh man, there's a study 2 years ago that showed that 40 kilometer was the range at which the covariance between glacier areas goes to 0. I apologize, I'm not a glacier modeler. I forgot the name of the study.
I think it's Sheen et al. David Sheen.
Yes, there you go.
Work with him and others, yeah.
Thanks a lot. So that work, I think, is the reason why we zoomed in on 40 kilometer. It was really not about whether the GlacierMIP2 results have a huge level of uncertainty or not. It was really in terms of our future idea is to include full covariance matrices in our probabilistic approaches. And so we really wanted to capture that covariance matrix to have the full content of the statistical uncertainty. And 40 kilometer to us is something that looks about right. And when you look at the RGI Randolph Glacier distribution at 40 kilometer, I think we captured that fairly well. I mean, it's highly debatable. We could probably go to 20 or 10 kilometer. Our mesh allows for that. And indeed, when you look at, sorry, let me go back the other way. Here, I feel mildly satisfied. I think we need to increase here. The Randolph Glacier is I mean, we've done a better job on Greenland than on the Randolph Glacier inventory. The whole thing is, though, a trade-off in terms of computational capabilities. We're kind of pushing the envelope here at 250,000 elements, 250,000 elements. This, if you want an idea, represents a 0.3 degree lat long resolution, which is not bad. We could probably push this system up to 500,000 elements, maybe 0.2 degree lat long equivalent, but we're really straining the NASA cluster right now. We're working with optimizations. Matthew has helped a lot optimize the solver. So long answer, I think 40 kilometers our target. Will probably reduce the resolution in areas where the GlacierMIP2 results are more solid. And as you said, no need to expand too much computational capabilities in areas where we're not really confident, but this will show up right away in the statistics of the model runs, and so and in the covariances also. So we should be able to capture that no matter what.
Okay, thanks. Jack Dibb has his hand raised. Sorry, I missed it. I don't understand why Zoom doesn't move the hand raisers to the very top of the list. Jack, do you want to pose your question?
Yeah, sure. This is probably a poorly posed question, but this is a really fascinating work, and I appreciate your focusing on the cities, but I guess my question is, if you're I don't know, a city planner or an engineer wanting to prepare for sea level rise, how does this help you? I mean, let's say you're in New York and you said that we should be really worried in New York City about what's going on in West Antarctica. but that if there's massive loss out of Jakobshavn in southwest Greenland, that would be good. You just hope that the right glaciers go at the right time, or do you think people might try to do some kind of crazy geoengineering? So if Thwaites lets go, does the U.S. throw a lot of something at Greenland to make it let go too and save New York? I mean, what's the utility for a planner or a mitigation of this great, I mean, really impressive understanding, but how do you use that information?
I'm not sure you use this directly at the coastal planning level. Coastal planners really use the NOAA climate assessment report every year anyway. What you do is you try to kind of inject that understanding at the NOAA climate assessment report level. That's where you need to go hit. And we're not saying use gradient fingerprints and have the coastal planners use that. That would be catastrophic in my opinion. But it still remains that if you're in New York or New Jersey and you see studies about Jakobshavn reverses its trend, you got to take pause and think, I don't care. It really doesn't concern me. That's the reality. And so it gives you a little filter on where you should look at. We're not actively advertising this to the coastal planning community. It's never been the intent, but I think we're trying to improve the understanding of why things are going on the way they are in every city. If you're in the south coast of Africa, South Africa, you really want to understand that gradient fingerprint mapping because you're really in the worst spot in the world. And if you don't see that gradient map, you do not understand why. And so there's, for every country has a different assessment report, right? So for us, we're really trying to, through the NASA Sea-level Science team, kind of inject some of this state-of-the-art research into hopefully the next NOAA assessment, and then that will be really useful for climate, for coastal planners. I have no pretension of doing anything else right now.
Thanks.
Good, thanks, Jack. So I think we'll wrap it up there with questions for Eric. Thanks again, Eric, for just an overview, an incredible amount of work, and really moving quickly to something operational and very accessible to everyone. It was very interesting. I do want to take the opportunity again to Caitlin and I to plug the 5-year plan that we're putting together for the Glaciers and Sea-level Collaboration Team as part of what IARPIC is getting set up for 2022 through 2027. So currently we're operating under the 2017-2021 plan, and we're right now soliciting input for what will be in the next plan. And why should you care about this? Just one example, I showed this last time, it does matter. If you've looked at the NASA Cryospheric Science Call due at the end of July, you'll know that one of the plans that's referenced for where you can come up with support for the science that you want to propose is the IARPIC 5-year plan. So this is one of your, frankly, several opportunities, but a good one to contribute to the state of knowledge and the assessment of what we want to prioritize in the near term for the glaciers and sea level community. So I think Caitlin is sharing the Google Doc, which is live, that you can all access and potentially comment on. There's some intro, which cites some of the same studies that Eric did today on why we care about the mass balance of glaciers and ice caps and the Greenland ice sheet. I think that's not a hard sell for this audience, and just highlighting the current state of research. And then the way that IARPIC is currently framing the 5-year plans, we divide what we want to focus on into objectives and then specific performance elements that represent goals, deliverables that we hope to achieve within the realm of the 5-year plan. Now, some groups approach this differently. Others sort of list a series of longer term objectives that we want to head toward that are sometimes less tangible. For what Caitlin and I inherited from this current plan, we didn't write this current plan. Most of these are more tangible, more accessible, and some of you will recognize your contributions to these previously. And Caitlin and I have taken the first stab at updating it and making it current and consistent with the missions that are operating, the types of research that people are doing now. But Caitlin and I are two folk somewhat tuned in to what's going on, but not everything. And we could use your help in helping improve it. So any questions on the 5-year plan? Oh, and I said to 2027, but it's actually 2026.
I guess I was just curious, if you're assuming they're going to keep about the same level of, at the high end, the 9 goals in the plan, because there was a meeting where I think Simon was saying that it's not even clear that there could only be 2 or 3 goals and then sub-objectives. And so you guys are going really granular, and I thought it wasn't even clear the overall framework was going to be similar to the current plan.
So it is true that the current plan and that framework could evolve. But we have to sort of draft what we think would be appropriate for this by an early July deadline. So we have to operate under the assumption that the framework won't change so significantly that it would dismantle what we prepared. Twyla's asking, can we iterate the timing deadline? By the end of this month is essential, because I think it's the first week of July that Caitlin and I have to resubmit this plan to the team. But yeah, but Jack, you raise a good point. As with many things like this, it could potentially evolve in a way that's difficult to predict.
And yeah, Joe,
But,
if I could, sorry.
Go ahead. No, go ahead.
I just want to pipe in really quick. Thank you, Jack, for bringing that up. And it is true that the structure of the IARPC 5-year plan is up for discussion. And so I think the strategy that Joe and I have been following is that the more formalized and well represented the land ice and sea level research needs are, then the more accessible they will be to the people sitting in the room making the decision on how the plan will be structured. So, and I was sitting in the same meeting that you're referring to, and I was a little bit concerned at the lack of explicit mention of physical science. So I've actually been entertaining the possibility of coupling our work on the 5-year plan chapter that we've advertised here, that we're seeking all of your input on, with maybe a formal federal registry statement as well, just to underscore how critical it is that we have the sort of expertise that we've enjoyed hearing from Eric today represented and kind of accessible to the people who are thinking about the really, really big picture. So thank you all for showing up for these sorts of webinars, and hopefully not only is it helpful for your own science, but it also helps program managers and other folks who are connecting the dots on where resources end up to see what we really have to understand and know in order to address the physical Earth system.
Yeah, thank you, Caitlin. And let's see, I just want to, so I think we'll wrap it up there. Thanks again to Eric for presenting an impressive body of work. We're going to take a break for the Glaciers and Sea Level team for the month of July, but we'll very likely be back in August. So look forward to that. If you are a participant and you'd be interested in presenting what you're doing to our audience of glaciologists, climate scientists, and government scientists from the US and around the world, let us know, and we'll see where we can fit you into one of our themes. And yeah, really appreciate you all joining. I know your time is valuable, and yeah, always fun to hear what folk are up to.
And congratulations to Eric's son on graduating.
Thank you.